Good morning and happy Wednesday to everyone. Today we're going to wrap up the equations of second order with constant coefficients. We're going to look at the superposition principle. It's much simpler than the name suggests. And the physical phenomenon of resonance as it can be understood through the solution of a differential equation. And then we're going to look at the method of variation of parameters. A very clever method. Before I get started, are there any questions, please? Okay, so the superposition principle is a very simple principle that says the following, that if you have a differential equation like the ones that we have been studying, so we have been looking at equations of the following form, and the right-hand side happens to be the sum of two functions, and of course, the method here is, and here's what I would like to say. Here's why I'm saying the sum of two functions. This sounds like an ironic statement. Anything is the sum of two functions, right? I mean, just add plus zero. But no, what I mean is that imagine that you have two things that look radically different. So you have, let's say, an e to the t, and then you have a cosine t. Okay. Why am I saying this? Because we know how to prescribe cosine t, how to prescribe a special solution of the non-homogeneous equation for the case that the right-hand side is cosine t. We know how to do the same thing for e to the t, but what happens when we have the sum of the two? And pretty much the superposition principle tells you, break this into two problems. So find a solution for this. So let's say this is y special 1 of t. And then find a solution for this. So call this y special 2 of t. And then the special function for which you want to use is the sum of the two. Okay, so pretty much what this says is, if you and this is just a matter of convenience, so that when you use the method of undetermined coefficients, you don't have too many unknowns. So you solve the problem separately. You determine the unknowns in one case, you determine the unknowns on the other case, and then the coefficients in the one case, you determine the coefficients in the other case. You make your life easy by working with one function at a time, and then in the end you add them up. Okay, and that's pretty much what it is here. Okay, so that's the superposition principle. I think in on today's homework I have one such problem just to illustrate it. And that's all. I mean, it's that simple. Any questions here, please? However, I would like to finish our journey in the world of second order equations with constant coefficients with a very interesting application. So take a look at the following situation. Imagine that you have a mechanical system that is described by a second order equation, like this one, for example. Okay, so let's say that you have, and give me a little bit of license here, and let's say that we have something like this. Okay. So this is, let's say, a insulated mechanical system. There are no external forces. Okay, so let's say you build a bridge. I would like to talk about the example of a bridge, and you will see why. So imagine that you build a bridge, and you try to understand what will happen, how this system will oscillate. I mean, certainly there will be oscillation. You know it when you cross a bridge in a car, you always feel a certain oscillation, right? So here, if you were to solve this equation, you would find that the oscillation will happen according to the following function that you will find: cosine of 3t plus C2 sine of 3t. Okay, and it will have a certain amplitude, and you can always sort of predict how the mechanical system is going to behave, and you have to build it so that it can withstand that oscillation, the oscillation with a given amplitude. So far, so good. So I'm just interpreting one equation, albeit in a very, very simple way, in an oversimplified way. But here's what I would like to bring to your attention now. Imagine that now there are external forces. So let's say you have wind. All of a sudden you have a wind, and the wind introduces an external force into our system. And that external force, in terms of the mathematics, is being expressed by a second order equation, which is non-homogeneous. So imagine that you have something like this. Imagine that you have something like this. And, if, let's say, the force follows something like this, so 2 cosine 2t. So I'm focusing on the frequency, right? So the frequency here is reflected by the number 3, right? And here, the frequency on the other side is reflected by the number 2. If you were to prescribe the spatial solution here, how would you prescribe it? Let's go over the process that we described last time. So you would say, what is the implied algebraic root here? Meaning, what is the root of an auxiliary equation that would force you to come up with cosine of 2t? And the answer is 2i, right? So that's the implied on the right. What are the actual roots on the left? And the answer is the actual roots on the left are plus or minus 3i. Is there coincidence? No, there's no coincidence. So how do you solve this? You just prescribe your spatial solution to be a cosine of 2t plus b sine of 2t. So far, so good. This is the standard process that we described last time, right? But now, here comes the difference. Now, imagine that external force happens to have the same frequency. So it's cosine of 3t. And what's the difference now? If you ask what the implied is, what the implied algebraic root, meaning the algebraic root that in an auxiliary equation would have forced you to consider cosine of 3t, then the answer is 3i, right? And now you have coincidence. And what does that mean? That means that the spatial solution should be this and you have to adjust by a factor of t. And what does the factor of t now signify? As t tends to infinity, this function does not even remain bounded. What does that give us in the sense of the mechanical, in the situation of the mechanical system? That pretty much our mechanical system will oscillate with a theoretically larger and larger amplitude, and eventually it will get destroyed. And you can actually find videos online on YouTube where bridges are being destroyed by the phenomenon of resonance. And what I want you to understand is that even if you don't have the exact same frequency, if the external force has a frequency which is pretty close to 3, you will still not need to do any adjustments, but the amplitudes that you're going to get in terms of these coefficients A and B are going to be really, really large. And they might have the same effect. So engineers have a very delicate task here. They need to study the system. They need to predict what the possible frequencies are going to be, and they have to build it, they have to implement it in such a way that no such catastrophic coincidence will ever occur. And as you can see, this is not something that can be achieved that easily. And in the past, this has, not necessarily predicted in the most successful way. And there are incidents of bridge collapse, even as late as I think this century. There is, where was it? Was it in Tennessee? I think. I mean, we can search, but in the last 2 years there was a major bridge collapse. Okay, and in most cases you have situations like this that will be the underlying issue. Questions, please. Okay, so now we're going to describe the method of variation of parameters, because there should be a very significant and simple question that is in the air here. And the question is the following. We have said how we can find a special solution in the case that the right-hand side looks pretty much very similar to the kind of equations that you get, to the kind of functions that you get when you solve such linear equations, such homogeneous linear equations. But what happens when that is not the case? What happens when you get a solution, when you get a right-hand side that has nothing to do with such functions? What do you do then? And the idea is that the normal prescriptions are not going to work. And pretty much the method of undetermined coefficients that we described last time is out of the window. And there is nothing we can do. But there is a very interesting method here, which, if we dissect it, we will realize that it's pretty much the algebra behind it that does the miracle and allows that method to work in such a seamless way, at least in favorable situations. And I don't want you to forget that. I don't want you to forget the fact that when we solve a differential equation, it's always a game of luck as to whether you're going to get, even if you have a sound method to solve it, whether you're going to get an integral that you can actually compute. We said from day one that finding the indefinite integral of a function, finding the antiderivative of a function, is actually a way to, is a special case of a differential equation, right? And if you ask yourselves, if somebody gives me a random function, can I find its antiderivative in a direct way? The answer is no. I mean, you have to realize that the exercises that you were given in Calc 2 were all very well chosen so that you won't get a function whose antiderivative cannot be explicitly found. Okay, you never got e to the x squared. You never had to wonder what is the antiderivative of e to the x squared, okay, or sine of x squared. I'm giving you two examples of functions that do not have an antiderivative that can be easily found. You never had to deal with any of that, right? But it's the easiest thing for anybody to produce a function for which you will have no clue how to find the antiderivative. The antiderivative theoretically exists, but you cannot find it. So think of the analogy in the case of differential equation. That's exactly what happens here. The antiderivative perfectly exists, but we cannot find it. Or the solution perfectly exists. One can show theoretically that the solution exists, but finding it might actually be reduced to, let's say, finding an integral that is impossible to compute. And that's what we're going to experience today. So we're going to give a method that, at least theoretically, it should be able to find for us a special solution in the case when the right-hand side is anything. But in practice, the right-hand side has to be chosen so carefully that, the whole method is pretty much works in practice very rarely. Okay. As usual now, and you're going to see this, I'm going to summarize how the method works. And here you have two choices. Either you will memorize a formula that gives you the solution that depends on some integrals I'm going to show you now, which is not what I suggest, or you're going to learn this outline, which it will take you literally a couple of minutes to remember and write it down, and you will be able to solve your equation by using less things to remember. let's look what the premise is here. So the premise is the same that we have seen in the method of undetermined coefficients, meaning you have an equation that looks like this. So the right-hand side is your typical equation of the second linear equation of the second order with constant coefficients. And the left-hand side is a function of t, but not one that you can recognize in the context of how the method of undetermined coefficients works. Okay, the first step is the same. So you solve the corresponding homogeneous. So you start by solving the corresponding homogeneous. And assume for a second that the solution of the homogeneous equation is C1 y1 of t plus C2 y2 of t, where y1 and y2 are the usual functions that we have considered in this context, and they're linearly independent. One is not a multiple of the other, and everything works pretty nicely here. Okay, so the stuff that we have seen. So now the idea is the following, that we prescribe a special solution of the form oops, why is there a equality sign missing here? I don't know. G1t y1t plus G2t y2t. Okay, let's observe what is going on for a second. So you take the solution of the homogeneous, and where you expect to get those constant coefficients, you replace them by functions to be determined. So these two are functions to be determined. So in other words, you vary the parameters. I could call C1 and C2 just parameters that for any initial value problem are supposed to be determined. And I'm varying those parameters, hence the name of the method, variation of coefficients, variation of parameters. So we're supposed to find those functions. And here's what I would like to say, that this is why I mentioned before that it's really the algebra of how we're going to manipulate this that is hidden behind this method. Because you know what, if somebody tells you, if you have the flexibility to use any functions you like here, G1 and G2, how restricted is the form G1 of t, Y1 of t, G2 of t, Y2 of t? So do you actually get any special functions by looking at this? And the answer is absolutely not. I mean, any function in the world can be written as G1 of t, Y1 of t plus G2 of t times Y2 of t. Okay, so anybody who thinks that, oh, okay, the crux of this method is that we consider a much more restricted type of functions and look for special solutions in that form, I will disappoint you, because pretty much any function can be written this way no matter what your functions y1 of t is, y1 of t and y2 of t are. So it's really the algebra that brings up a very nice situation that we're actually taking advantage of in order to determine G1 and G2 that work this way. Okay, it's not that you need to know what I'm saying in order to apply this method, but sometimes it's good to look behind these things and realize that we're not doing something extremely exceptional here or very clever from the point of view that we're considering some very special function. No, we're not considering anything special here. If you will, it's the algebra that brings up a very fortunate coincidence that eventually solves the problem for us, at least in simple cases. Okay? Any questions before I show you the algebra? This is the point where I would like to show you how the algebra works. So, from a strict point of view, what you expect me to do here is actually find the first derivative, find the second derivative of this prescribed function that I gave you, plug it into my differential equation, and try to figure out what G1 and G2 are. Okay, that's the simple-minded approach. This is what we expect to do. Okay, now if you do that, I want you to reflect for a second what this task entails, because we're going to get something pretty convoluted. Can anybody tell me why I'm going to get something pretty convoluted if I attempt to take the derivative of this function y sub s and subsequently the second derivative? Can anybody tell me why I am warning you that we might get something pretty convoluted here? The reason is
this because C1 equals C2?
No. We're not working with C1 and C2 here. See, we have replaced C1 by a function, G1 of t, and we have replaced C2 by another function, G2 of t. And
Because
theoretically speaking,
G12 equals G2t. So the two functions is the same?
No, they're not going to be the same. They're not necessarily going to be the same, and you will see this in different examples. What I'm asking is, why are we going to get a pretty convoluted expression when we attempt to take the derivative of y sub s and then the second derivative? And pretty much the reason I'm looking for is that the product rule is going to kick in, okay, and it's going to give you, a lot of stuff here, right? I mean, if you try to take the derivative, you will have to apply the product rule twice. I'm not saying that the product rule is something terrible, but the second time you will try to apply it, you will get something pretty complicated. And this is where the great idea of this method lies, because here's how you do it. Let's find the first derivative. Okay, so what is the first derivative? It will be, according to the product rule, G1 prime of t times y1 of t plus G1 of t times y1 prime of t plus G2 prime of t times y2 of t plus G2 of t times y2 prime of t. Okay, it will be this, right? And now, remember what I told you in the beginning, that this whole setup is not restrictive for what y sub s can be. It can be anything pretty much. Exactly with the thought that it's everything, the brilliant idea of this method is to ask right from the get-go that G1 prime of t times Y1 of t plus G2 prime of t times Y2 of t is equal to 0. So we require this. And again, there is no particular reason to do this, but it's pretty much the implicit flexibility that we have in working with something like this that allows us to do this. So this is the first condition that we require. We require this. And all of a sudden, our life becomes much easier because now ys prime of t ends up being g1 of t times y1 prime of t plus g2 of t times y2 prime of t. And now we can find the second derivative, and it's not going to be that horrible. So you will have g1 prime of t, y1 prime of t, plus g1 of t times y1 double prime of t, plus g2 prime of t times y2 prime of t, plus g 2 of t times y2 double prime of t. Okay, so now we have our two derivatives. And what we do is we plug them into our equation. Let's not forget that this is our initial equation. And if we do so, what do we get? We get a times the second derivative, which is what I just found, g1 prime of t, y1 prime of t, plus g1 of t, y1 double prime of t. Maybe I shouldn't have put of t all this time. You know, I would have made the whole thing a little simpler, but you know, my apologies. Plus b times the first derivative, which is g1 of t, y1 prime of t, plus g2 of t, y2 prime of t, plus c times the function, which is g1 of t, y1 of t, plus g2 of t times y2 of t. And this should be equal to f of t. Okay, that's what we get. And you might think to yourselves, you must be kidding. This is still pretty convoluted. Yeah, but wait for a second. Okay, wait right here, because take this and then take this and finally take this. Do you notice what happens if you take the yellow stuff? What do we get if we put together the yellow stuff? Don't we get a g1, or I should take out actually g1 of t as a common factor. G1 of t times a, yeah, exactly. You guessed it quite right. So you will get a y1 double prime plus b of t plus b y1 prime of t plus c y1 of t, right? If I get all the yellow things that I have underlined and I factor out the g1 of t, what I get in there is this parenthesis. And can anybody tell me what this parenthesis is? Because it's something very, very simple. And why? What is this parenthesis? I specifically am asking, what is this equal to? It's the homogeneous equation. And what was y1 to the homogeneous equation? What was y1 to the homogeneous equation? How did we choose y1? Y1 is not just any function, right? It's what? It's a solution to it. So what does it mean that it's a solution? This thing is zero. This thing is zero. Okay, so it disappears. And for the same reason, if you do this with y2, what else are you losing? You're losing this, and this, and this. So the yellow things will give you zero, the red things will give you zero. And the question is, what is it that remains behind? And the answer is, after you lose all those things, you're left with A times G1 prime of t times y1 prime of t plus g2 prime of t y2 prime of t is equal to f of t. Not too bad, right? Not too shabby. That's not that complicated. And here's your second condition. Now, do you see first condition, second condition? We have to remind ourselves in these expressions what is known and what is not known. What are the known things? y1 of t, y2 of t, y1 prime of t, y2 prime of t. All of these things are known. What are the things that are not known? G1 prime and G2 prime. Can anybody tell me what can you think of when you look at this equation? What is it that you're looking at? I'm sorry, at these two equations. You're looking at a linear system. So you can solve this linear system. So we solve this system. For G1 prime and G2 prime. And let me rewrite the system because, you know, if I rewrite it without the t's, it's pretty simple to actually remember. So it's G1 prime Y1 plus G2 prime Y2 is equal to 0. And G1 prime Y1 prime plus G2 prime Y2 prime. And I can take the A over to the other side. So it's F over A. That's it, without the t's. Not too bad, right? It's not a bad looking system to remember. So we solve this system for G1 prime, G2 prime, and now we integrate. And integrate to determine G1 and G2. And therein lies the difficulty. Okay, so what is the difficulty here? Up to this point of solving the system, there's absolutely no obstacle. You can do it, no questions asked. Anybody can do it, everything that I have outlined so far. The determinant of the system is the Wronskian. So the fact that the Wronskian is non-zero tells you that this system is going to have a unique solution. That's a very good remark. Yeah. So the known quantities here, the question was, is this related in any way to the Wronskian? And the answer is absolutely, because the known quantities here are what? Are these red things that I'm underlining. And if you take the determinant of these red things, that's exactly the Wronskian. So the fact that the Wronskian is non-zero tells you that this system will have a unique solution. Okay. So we determine G1 and G2, and I'm saying we integrate. Okay, this is the only real obstacle. Okay, who tells you that the integrals that you're going to come up with after using this method can be actually computed? And the answer is nobody. Nobody guarantees this. So we have this other paradoxical situation that if I'm the one, for example, who prepares an exercise for you, I have to be very careful in what I'm choosing to give you. So if I just choose anything, so let the right hand side be anything you like. Okay, ln of t over t squared plus 1. Okay, I just gave you this from the top of my head, right? Let's say that I choose f to be ln of t over t squared plus 1. Okay, good luck computing those integrals. The integrals you're going to get are going to be impossible to compute. Okay, so both the differential equation and what you have on the right-hand side have to be chosen judiciously, but this is not business of yours. I'm going to be the one worrying about this. Make sure that I choose something that will eventually enable you to solve it. But regardless, that's the task at hand here for me when I prepare such a problem, not for you. So what am I suggesting? I'm suggesting that you remember this system. That's all you need to remember. Then you solve the system, you find G1 prime, G2 prime, you integrate G1 prime, G2 prime, and then you have your special solution. Okay, and we're going to do an example after our break. Okay, so let's take our break now, and we're going to answer questions when we come back. Okay, so welcome back, and let's do an example. Okay, are there any questions before I proceed with the example? I would also like to add here that there are some other cases of equations of second order that we're going to see that are kind of different. So you have to start building a sort of experience for yourself, so that when you are given an equation like this, you can identify it as the method of, as pertaining to the method of variation of parameters. So what are the things that you should be looking for? And let me give you an example, and let's discuss. So let's discuss, when we're given such an equation, how we're going to recognize it. What are we looking for? So here is our example. Find the general solution of y double prime plus y is equal to secant t. Okay, let's solve this equation. So how do I know? Look, let's suppose that, you know, I'm not giving it to you as an explicit example of the method of variation of parameters. How do I know that I have to use this method? So first of all, it's a non-homogeneous equation with a linear equation with constant coefficients of the second order. These are the equations we have been studying. The fact that it's non-homogeneous tells you that what you need to do is to find the general solution of the homogeneous, and then a particular solution, a special solution of the non-homogeneous, right? What methods do we know for finding a solution of the non-homogeneous? The method of undetermined coefficients. When do you use the method of undetermined coefficients? When the right-hand side, in this case secant, looks like a solution of some homogeneous equation of that type. Does it look like it? No. We never get secant of t in what we did. We get sines, we get cosines, we get exponentials, we get polynomials, we get polynomials times the things that I mentioned, but we certainly don't get secant. So that prompts you right away to go with the variation of parameters, with the method of variation of parameters. That's how it works. Okay. Questions? So that's what prompts you to use the method of variation of parameters. So, so what do we have? We start by solving the homogeneous equation. So we have y double prime plus y prime is equal to 0. There's no prime here. So this means that the auxiliary equation will be r squared plus 1 is equal to 0. R is equal to plus or minus I, which means that y of t is equal to c1 cosine t plus c2 sine t. Is everybody with me so far? Okay, we solved our homogeneous, so let's call this y sub h. We're looking now for the special solution of the non-homogeneous. Again, that's what we're looking for. So how do we find it? What I want you to understand is that in the system that I gave you above, this is your y1 and this is your y2. Okay, so let's form the system. What does the system look like? It will be g1 prime times cosine t plus g2 prime times sine t is equal to 0. And then g1 prime times the derivative of cosine t, which is negative sine t, plus g2 prime times the derivative of sine t, which is cosine t, is equal to secant t divided by a. A in this case is 1. I don't need to divide by anything. That's what I get. And that's my system. And from this system, I'm supposed to find g1 prime and g2 prime. Okay? Everybody with me? All right. So I will need a little more real estate in order to solve this system. So allow me to go over to the other page. Rewrite the system. And how in the world do we solve such a system? And the answer is just solve it the way we have solved systems of equations with numerical coefficients. So I'm going to multiply the first solution, I'm sorry, the first equation by sine t. I'm going to multiply the second one by cosine t. And when I do so, you see that the coefficient of cosine of G1 prime is going to be opposite of the coefficient of G2 prime in the second equation. And I'm going to add them up. So what am I going to get? I'm going to get G1 prime cosine t sine t plus G2 prime sine square of t equals 0. And then G1 prime negative sine t cosine t plus G2 prime cosine square of t. Oh boy, I get cosine t times secant t. But that's not too bad, right? What is cosine t times secant t? How much is cosine t times secant t? Yeah, that's one. See, we're in luck here, right? It's one of those examples that were specially manufactured for this method. So now we adapt. We adapt. The G1 primes cancel each other. And what you get is G2 prime sine square of t. And I can actually take it as a coefficient. Plus cosine square of t is equal to 1. Of course, the Pythagorean theorem kicks in here and gives us G2 prime is equal to 1. Not too bad, huh? Not too bad, because if G2 prime is equal to 1, what is G2? It will be the integral of 1, which is simply t. And here, of course, again, some of you might say, well, where is my c? I lost points in Calc 2 for not putting plus c when integrating. Yeah, but here you have a similar situation to what we saw before with the integrating factor. You just need a function. You don't need the most general function. So we just give ourselves G2 to be just t. Okay, and then now you want to find G1. How do you find G1? You simply appeal to the first equation that has G1 prime and G2 prime. You know that G2 prime is 1, so now you plug it in and you get G1 prime times cosine t plus G2 prime is equal, plus sine t is equal to 0, which gives you G1 prime is equal to minus sine t over cosine t. Of course, you know this is tangent, but after all, it's much simpler to integrate it like this. So I'm going to get G1 is equal to the integral minus the integral of sine t over cosine t. Do you all remember how to find this integral? It's substitution, right? It's u is equal to cosine t. And du will be minus sine t dt. So you have the minus sine t right there. And this will be du over u, which is ln of absolute value of u. Again, I can put plus c, but get rid of it right away. And that's eventually ln of absolute value of cosine t. And that's your G1. That's your G1. So you have your G1. You have your G2. Or you have your G2, you have your G1. It's important that you put them in the right places. Okay, you cannot just shuffle them around and put them anywhere you like. So now I can give my special solution, ys of t. It will be what? The way I prescribed it. So it's going to be ln of absolute value of cosine t times cosine t plus t times sine t. Not an obvious solution to figure out, right? I mean, this is by no means something obvious. Okay. it's not impossible to figure out. We have our special solution. Our problem does not end here. What do we need to do? We need to add it to the solution of the homogeneous. So now we can give the answer to our problem, which is y of s is equal to c1 cosine t plus c2 sine t plus ln of absolute value of cosine t times cosine t plus t sine t. And that's it. That's it. Okay. It's a very nice method when it works. It's a really beautiful method. Like I told you, the big deal here is, can you compute the integral? So you determine g1 prime, you determine g2 prime. Can you find the integrals? I love these questions. So cosine is an even function. Why do we have it in absolute values? So can I remove the absolute values? These are really, really nice questions. No, the answer is I cannot remove the absolute values. Even function doesn't mean positive. Even function simply means that its graph is symmetric with respect to the y-axis. So, here's an even function. Okay, it's not positive, right? Okay. And there was another question. Why is y of s? Ooh, yes. Thank you. Oh my gosh, I'm getting too old for this. Thank you. Y of t. Yeah. Okay. And that's it. Now, so look at the whole method. I mean, hopefully in any particular example that you will have to solve, it will be as hospitable as this one example, because otherwise things can get, as we said, pretty bad very quickly. So, so this was not a bad example. This was definitely not a bad example. But examples from this kind of method can get pretty convoluted. However, I guarantee you that you're not going to find an example where you cannot integrate g1 prime and g2 prime. So that's a promise. Are there any questions? Let's take our attendance. Let's do it. I want you to give me for attendance today the result of 3 plus 5 times 10. I want you to find how much is 3 plus 5 times 10 and give me the result. Okay, I'm just kidding. This is a joke, right? We all know that multiplication goes first. So nobody said 80. Okay. Yeah. Oh, okay. Now, now should I give you? Oh boy. Yeah. I know. I didn't, you know, I mean, obviously, answering this the wrong way should not deprive you of your attendance, right? So you could say 80 and then still claim your attendance because you're here, right? I mean, so yeah, okay. So maybe I'll give you something more interesting on Friday. Now, let's discuss a little our. I'm going to. No, I was about to end the recording, but let's discuss the exam on record so that everybody can hear it, even if they're not in the session today. So let's do a little bit of planning. Somebody reminded me of the exam during the break, and I think it's a good idea to look at it. Okay, so what do we have? So first of all, if you go to your study guide, you can see midterm exam study guide, right? So everybody go on Blackboard and open up the exam. Now you will see that this study guide has how many are there? I think it's 10 problems. 11 problems, and most of these problems we have already done. So I think it's the last 3 problems that we haven't covered yet, which we will cover by next Friday. So your exam, how many problems am I going to ask you to do on the exam now? I think the answer is 5 or 6, but let me take a moment and tell you exactly what to expect. Let me bring up my schedule. No, I actually, you're saying the less is better, and I beg to differ. Why? Why? I'm not saying that I will seek to give you a long exam, because when you miss a problem, the contribution of that mistake becomes more significant. So don't automatically think that a smaller midterm exam is actually better for you. So that's not necessarily a correct assumption. So I'm going to give you 7 problems on the exam. Okay, 7 problems on the exam. So the first problem. So now look at the study guide. So the first problem will be either a okay, so I should say the first 2 problems are going to be taken from the following mix: Euler's method, separable equations, exact equations, and linear equations, and Malthusian model. And yeah, Malthusian model, not any population model. So let me write this down. Okay, let me write this down so that everybody can see. So example. So first 2 problems are taken from the following mix: Euler method, separable equation,
Recording in progress.
linear equation, exact equation. And Malthusian model. I'm not even asking you to look at the
Recording in progress.
at the my brain stopped. I'm going to say that I don't want you to look at compartmental analysis. So I'm leaving compartmental analysis out for this example. Then problem 3 will be second order homogeneous constant coefficients. The joke of the day, right? Simplest thing around. Problem 4 is going to be undetermined coefficients. So there will be a problem from undetermined coefficients no matter what. Okay, and then you may or may not have an adjustment, but there's going to be such a problem. Problems 5 and 6 are going to be taken from the following mix. So we have variation of parameters, which we saw today. Reduction of order that we will do on Friday. And Cauchy-Euler that we will also do on Friday. Okay? So problems 5 and 6 are going to be two problems of this type. And if you look at the study guide, you will see that they're illustrated by problems 7, 8, and 9. Problems 7, 8, and 9 of the study guide are exactly like this. Okay, so every problem on the study guide is, every problem in the mix is represented in the study guide by one problem to show you what to expect. And finally, the problem 7, it will be a problem to compute Laplace transform. To compute a Laplace transform, you don't know what that is yet. But again, it's going to be one of the quickest problems to solve on this exam. So if you count how many these problems are, so let's count them. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? That's exactly how many problems you have on the study guide. Good deal? So the study guide gives you exactly the types of problems that are possible on the exam. I'm not going to give you 11 problems, though. I'm going to give you just 7 problems, and I showed you how I'm going to choose them. So I'm not going to choose, not going to give you a separable, a linear and exact, no, and a Malthusian model. No, I'm going to give you just 2 from that mix. I'm going to give you for sure a homogeneous equation with constant coefficients. I'm going to give you for sure a problem of undetermined coefficients. I'm going to give you 2 problems from variation of parameters, reduction of order, and Cauchy-Euler equation. And finally, I'm going to give you 1 problem to compute the Laplace transform. Okay, I think it's very, very concise. And you know, we have already seen, I want everybody to do well. Okay, and I'm trying to make it as concise as possible. And if you look at what I gave you here, pretty much I'm telling you I'm going to give you one of everything. The only thing that I'm leaving out from your review is the compartmental analysis. And if you want, I mean, in the very beginning that we did the implicit solutions and whatnot, I'm leaving those things out. So all of these items we have seen so far, we'll see this on Friday, and this will be on Monday. Okay? And that's it. That's your exam. I want everybody to do well, but as you can see, you need to start preparing right away. Okay? Does anybody have any questions, please? So if you ask me about the exam again, I'm going to just refer you to this end of the recording because I gave you everything in detail. You have the study guide. It has examples. No, don't worry about this. I'm going to give you a nice printout. No, I'm not going to start writing the problems with my chicken scratch on Zoom and expect you to. No. I'm going to give you a nice printout, and you can either print it out and use that, or just do the problems numbered on piece of paper. The important thing to take into consideration here is that you will have 1 hour for this. You will have 1 hour. That's how long you will have. Those of you who have extended time, please book your exam at the DRC and don't tell them it's an online exam. I will send it over to them and you will take it in person at the DRC. It's not going to be online. Okay? You know what? Great question. How many points? So this exam, this midterm exam is going to be out of 70 points. So all points are going, all exercises are going to be equivalent. Okay, so for all intents and purposes, there will not be one problem that is worth more than the other problem. So all of them are going to be equivalent. Okay.
So how exactly is this going to work? Like, are you going to send us the exam before class, or are you going to send us the...
right at the beginning of time, I'm going to email you the exam and also post it on Blackboard. You will have a couple of minutes to either print it or copy the problems, and then you will need to take it without making sure that I can see, everything that is going on around you. So the supervision, the proctoring is going to be the same as it is for quizzes. But please understand that I will be much stricter regarding, your cameras being well in place, and make sure that you don't look around, that you don't have things of ambiguous nature around you. So please understand all those things, because I really don't want to bother anybody during the exam. But I told you before that last year I had somebody who was obviously looking at notes. It was obvious. I mean, you cannot hide. Okay.
Can you put each one in such as a separated room? So my point that if you like to speak to someone for some reason, it's not affected the others.
Yes, in a perfect world, that might be right, but I'm not going to do anything like that. I'm not going to create rooms or anything like that. I hope that there will be no such need. Also, if something like that happens, hopefully it's going to be quick. Okay, so my apologies in advance for anything that may happen to distract you. But no, I'm not going to have rooms or crazy things like that for something as simple as this. Okay. Are there any more questions? Kirill, can you come to my office hours for this question, please? Here, you may need to adjust here. No, 280 plus b is not going to work. Corresponds to what? Since no. It's no, you will need an adjustment. So please see me during my office hours. Okay, so that we can discuss this. Okay, that will be all for today. Have a great day.